The first picture here are the two domes in Big Bear. The one on the left is now the synoptic dome, and on the right is the dome that houses our 1.6 meter clear aperture Offaxis telescope. And the blank that was available to us from SHOT was actually 1.7 meters. And so that's what we bought. And we lose 5 centimeters around the edges for clamping. And in the process of the building, we have an insulated dome painted with a goldstone number 5 paint, and the temperature on the dome all the way around is different everywhere. So like on the downside, it sees the temperature of the lake, and on the sunny side, it sees the sun, and up on the top, it sees the temperature of the clouds. So it's good that it's insulated. Anyway, the dome sits in the middle of the lake, and there's 2 miles of open water to the west. The prevailing wind comes from the west. The lake is cold, so we have a nice laminar flow that limits the ground scene, and that's the purpose of putting the telescope in the lake. And the telescope, the observatory was transferred from Caltech in 1997, and in 2003 we started the GST project, and we got first light in 2009. Our first AO corrected images were in 2010, and those were with the old AO 76 system, which was a joint NSO KISS Big Bear project. Unfortunately, the AO was for half-meter class telescopes, so it was really only good in the infrared for a 1.5 meter telescope, but it was a heck of a lot better than nothing. And then we built AO 308, which had a 357 actuator DM, more or less. And we wanted to be in charge of our own destiny, so we built our own system, which is now replaced. And then in 2014, we began the same collaboration in multi-conjugate adaptive optics. And I'm told that there have been more than 150 publications using a GST data. So we're pleased with that. Now, you always have to justify yourself to the taxpayers. And so getting the light to the Goode lab was a $12.5 million effort. And, more or less, it's always hard to count. You have people who are doing one thing and doing another thing at the same time, and so how do you parse their time? But I think that's a fairly accurate measure of the cost. And then the instrumentation is actually more, and a good part of that is because the AO and the AO costs keep mounting as we do more and more AO work, and that's fine. That's the way it is. Now, I should say one more thing, that in the early days of getting the funding, we got some initial funding from the Air Force, but the first big funding was from the NSF. And Michael's help was essential for us. There was the force of his personality and the backing of him being director of HAO that was critical for us to get the money that really got us rolling. And I know I thanked you at the time, but I'm glad to thank you now as well. It meant a lot to us. And so thank you again. I think we first met in Catania in 1983. And I remember our first conversation, and I remember your big smile and your real enthusiasm for the science. For me, also that meeting was important for another reason, and that was my longest collaboration with Wojtek Jambowski, and that was in full swing. And it's appropriate, I think, to mention that now. Wojtek and I became like brothers after a 20-year long collaboration where we lived in each other's houses. And he turned 80 last month, so, and he's still very sharp. Now, yeah, he's very good man. I'm friendly with his sons, and they're both professors at the University of Warsaw. But I have to say, and probably you've heard this before, Michael, but when I first met you, I thought you were a dead ringer for the lead singer of my favorite German group, Steppenwolf, and I thought, that's John Kay in circa 1968. And, well, sorry, I couldn't help myself. So this is the suite of instrumentation that, that our telescope has. And we've had 3 generations of adaptive optics. And the current generation, it's all based on the KISS chaos system and the work of Dirk Schmidt, who's not here. You got him working even. You couldn't give him the morning off. Anyway, it was the single deformable mirror called Classic AO. We had a contest between our version and his version, and it was more or less a tie, except that his version was able to do a better job of selecting the KL polynomials. So anyway, we have a system that works, and the MCAO is now really ready to be a facility instrument. It holds lock for 3 DMs just as well as for single DM. So if the MCAO doesn't hold lock, then CAO won't hold lock either. And that's really saying something. We have a single Fabry Perot visible light spectrometer. It's just, we own a second Fabry Perot, but it's not put in. So our most mature instrument is an IRIS, it's a dual Fabry Perot spectropolarimeter. We also have a cryogenic spectrograph, and the cryostat holds all the optics, and it's sort of the size of a grand piano. It's a forerunner of CryoNERSP on DKIST. Michael and I are both co-investigators on that project that Thomas is in charge of. And we have built by our South Korean collaborators the fast imaging spectrograph, which does H alpha and 8542 at the same time for studies of jets. Now, why Offaxis? This is from a paper that I did with Jeff Kuhn and Gilles Moretto. And, you know, when we tried to do AO with the old half-meter telescope, we had a spider. And dealing with the spider, this is a 10-meter telescope in thermal emission. And so you can see if you have your primary mirror made of segments, only an issue for like the giant Magellan telescope. And for solar telescopes, having, oops, I mean to do that. You have the spider, and we always had trouble with the AO system. It never functioned as the way we would have liked it with the half-meter telescope with the darn spider. So that was our technology sacrifice in the building of the 1.6-meter telescope. It's easy, right? You have the spherical wave coming out of the interferometer. You have a computer-generated hologram, and it makes the aspheric of your primary. Well, there was about a year and a half that it sat in the Mirror Lab in Tucson, where we had all kinds of problems. We went through 3 generations of computer-generated holograms, and finally, problems were solved, and it was good because we also had a second test, the pentaprism test, and this null corrector was the forerunner for the GMT and the D-KIST null correctors. So there's always something good about being first. It didn't come into our critical path because the optical support structure being built in Longmont was also delayed because you may not remember, but there was a time about 2006, 2007 that oil was more than $100 a barrel, and then on the western slope of Colorado, every old oil well was opened up, and you couldn't get machine shop time anywhere in Colorado. So we were delayed, and so the mirror beat the optical support structure by a few months. So this is the polishing support. We had 36 actuators on the back, so we have active optics. So the idea and the advantage with Offaxis is you can sort of move it so that you can put most all of the residual air in the mirror into astigmatism, and then you can bend it out. And that's what we do. And it works quite well. The AO is Shaq Hartman. Nothing much to say about that. Now, our first AO corrected images were in 2010 with titanium oxide. And this is, where am I? Here. And we were pretty happy with that. This is AO plus speckle correction. And, but 3 years later, when we had AO 308, you can see that Strel really matters. And so what's good for 1.5 meters would work fine. Well, what's good for 0.5 meter isn't going to be good for 1.5 meters. But with the, so this is a 43-minute movie, and you can see all kinds of interesting things in there. So this is AO plus speckle correction. Most of the movies I'm going to show, there's no post facto reconstruction. Oh, please play. Oh, God. Now, this is a 10-830, so it uses AO 76. That's good enough because you're well into the infrared. And the 10-830, you see the individual fibers coming out and going into the chromosphere and coming back. They originate in the dark lanes. And what's interesting about this is at 2147, you'll see this event that occurs everywhere in the field at once. And this tells you you really want to have multi-conjugate adaptive optics because you want high time sequencing covering the whole field. Because if you do speckle reconstruction at exactly the moment that you want to know what's happening, the images are changing too fast so that the speckle reconstruction is too problematic to be useful. There are all kinds of other arguments you can make, but this is one I like. I think I don't need this one. This is just to say about ground layer AO, if all the turbulence, this I swiped directly from Dirk Schmidt's PhD thesis. If all the turbulence occurred at the ground layer, then you could have a wide field correction, full correction with a single DM, but that's not the case. And so you need more than one DM. Now, our basic idea was 3 DMs. Why 3? Well, very naively, we thought, look, one for the ground layer, one for the transition, and one for higher up. And we wanted to have a 70 arc second field corrected because that was the size of the spectropolarimeter in the visible. And we decided after some back and forth to have 9 guide regions. Basically, you can think of a tic-tac-toe pattern on the field of view. And so you have 9 guide stars or guide regions. It's about the same as Gemini South, which has 8, 5 laser guide stars and 3 natural stars. And ultimately, we wound up with a single wavefront sensor. So here's the design of the system. Boy, let's go back. So the light comes in from here, and then here are the 3 DMs, high altitude, mid altitude, and then the pupil. And then the wavefront sensor is over here, and here's the science camera. So we put the pupil DM closest to the wavefront sensor because we believe most of the action is going to be at the pupil. But you can argue that's an opinion. So what we did was we put a 4th DM in the path, and then we switched rapidly between having the pupil DM be the first one to see the light and the last one to see the light. And basically, there was no difference. Maybe there was a little difference in the case where the scene wasn't so good, but you were down in, I have to look and analyze the data very carefully, so the effects were small. And so we just keep the pupil DM closest to the wavefront sensor. And this double Z design had this advantage of, if you wanted to switch, we had the idea that maybe we would promptly want to reconjugate one of the high altitude DMs to a different altitude because something might be happening that's, hey, today's forecast says that there's more turbulence at 7 kilometers rather than 9. So you could take rats again. You could take and move one DM and its partner mirror and change the conjugation. It works over a certain range of a couple of kilometers. And basically, we haven't used that, but that's life. So first you go into the laboratory, and what do you see? Well, we put a cooktop in front of each DM, and then you have this pattern of granulation that you feed in. And you look at it enough times that I got used to, I knew all the granules in the pattern, and that's a bad thing. And in fact, I insisted on substituting another one in just because you get sick of looking at it. But it always worked. And then when we turned it on the sun, it never worked. Maybe marginally, but it didn't really work. So it was suggested to us, take the field of view, cut it from corrected field from 70 arc seconds to 35. The idea is the turbulence is really everywhere, not confined to certain layers. So if you narrow the field of view, then the corrected field for each DM will be deeper. And so we got continuous coverage from 0 to 11 kilometers in Big Bear. And so the mirrors conjugated the pupil to 3 kilometers and to 8 kilometers. And let's see, anything interesting here? So it's pretty similar to to the Gemini south, and 3 DMs does do better than 2. So it's worth having. But you can very easily get out of hand requiring too many DMs and too many guide regions, and then your inverse problem is going to be really nasty. But finally, 3 summers ago, I think this is the movie that Oscar showed, July 27th, there's a single DM, and then there's multi-conjugate adaptive optics. And this was the first experience I had of sitting in the control room after 20 years of sitting in the control room, where this is exactly the video that we saw that day. Nothing has changed. And as soon as you saw it, you knew it worked. Barring that it was a one-off, but of course it turns out to be very repeatable. So I would hope everyone would have that experience of, there it is, right in front of you while you're sitting there. And yeah, even after almost 4 years, I really like to look at this movie. It's my favorite. And so actually we missed one a couple days earlier, and because of this active region. But the point of showing this is, imagine the tic-tac-toe pattern of selecting out the 9 guide regions, and the code will just take whatever it's presented and use it. How am I doing on time? Okay. Now, in that setup, what we would do is take 150 images, say, of classic AO, then switch to MCAO for 150 images. So you can see the isoplanatic patch, pardon me, here. And then the ground layer AO sort of gives you a reduced correction over a wider field. And then, nuts. And looking at this generalized Fried parameter, which is the bright color, is basically that the wavefront change is less than a radian. You can see that the multi-conjugate adaptive optics roughly triples the corrected field of view. And so it really works nicely. Now, after 3 years, now we're looking in the blue, calcium K, and this is a 30-minute subset of 90 minutes of data, where you just after 90 minutes you've had enough. You just turn it off. It's not like you lose lock. And there's no post facto correction. The only thing that's done is image selection. And this is my favorite part that occurs right here. But you can look at this a lot of times, and then I looked at simulations by Stein and Nordland, and basically exploding granules, everything that they see, you can see in this movie. And so we improved the optical setup. We have a better, faster control computer so that it operates at 1,500 frames a second. Every little thing makes a big difference, but it's really stable, and it's a user instrument. So this is with a 1 nanometer pre-filter. And I must have watched this thing 100 times, and every time I watch it, I find something that I hadn't seen before. And then, here the scene isn't so good, but we borrowed 1/10 of a nanometer 10-8 calcium K filter, so we could see on the right, you see the chromosphere, and then it's titanium oxide on the left. And if you look and find any pattern in the bright points, you can find the same pattern in the plage everywhere. So, and again, no post facto correction except for frame selection. And the scene wasn't so good here. But there's a certain frustration too. The frustration is we don't have the magnetic field. So now we've set it up so that this summer it'll feed the light to this, and we will measure magnetic fields at the same time. You know, oh, you see that glitch? It lost lock, and it regained lock all by itself. So this, I like that, the fact that the scene wasn't so good, and so you can see what happens when it loses lock and regains it. It's all by itself. And now for a moment of a last poor Yorick time. We have a profiler for, for measuring the turbulence profile. It's on the horizontal bench. Anyway, that works at 500 frames a second. The exposures are 50 microseconds. And watching this enough times, you can really learn how a fly's wings operate. So it's a quarter of a second long. And yeah, I mean, I didn't realize that there's this. Anyway. Oh, this is, it's, part of the beam is sent off to a profiler to measure, using the slow-dar method to do triangulation, to measure the static profile. So we're not trying to control the AO. This is just simply to measure what's the turbulence as a function of altitude today. And so we're not, it's not fully operational yet. We're still analyzing to make it so that we can make it a user instrument where you just flip a switch and then the profile plot comes up for you. But it's a copy of what's from Gemini South. So, what's next? Well, as I said, we're going to feed the MCAO light to VIS, and that setup is all made and operates. We're just waiting for the weather, because you make these nice movies and you'd say, oh, that looks like this, but I don't have a magnetic field, so I can't do anything with it. And we also have a setup for doing the MCAO in the near infrared, and that's different. And I'm interested in that because now we have a setup with a 70 arc-second field of view, which is the same size as NIRIS. So then we can use our best instrument, and that's ready to go. And also off-limb AO. This was just using the current MCAO. Just basically, what does this show you? This shows you that the scene is Kolmogorov, so that you're going to get a much larger isoplanatic patch in the infrared. No surprise. And we did a lab test for the near infrared MCAO, but we did it with our old Rockwell camera, which only had a 60 arc-second entrance window. So we shifted it up so it's off center. But anyway, it worked. was quick and dirty. We needed it for the proposal. And the same thing about the Prominence AO, which is built on what Thomas and coworkers did at SAC-Peak. It worked a few years ago on the Dun. It worked. We took about a third of the center line H alpha, and we used that to lock. And on the right, you can't really see anything. The scene wasn't that good. And again, it's the same thing. It was in the same proposal. But you can look on the plot of the KL indices, and the errors of everyone are reduced. For those of you who don't think in KL modes, they're the orthonormal cousins to the non-orthogonal Zernike polynomials, but they're close enough to be the same thing. So that's another thing that we will do in the coming summer, and so we have enough to keep ourselves off the streets. And that's it. So thank you.